Welcome to the UGC lecture series. This is the EPG Pathshala lecture series on data structures. Now, in this module, we will be talking about the design of algorithms. In the previous module, we have spoken about the analysis of algorithms. So, these are the people who are who have contributed to the content. So, let us look at what are the learning objectives of this module. It is to understand the different algorithm design techniques, to know the type of problem that can be solved with different design techniques, and to take the same problem and explain how it can be solved using two techniques. Now, again this is a small module that explains design, but our course is on data structures, but still we should understand the design technique to understand how to choose the data structures and how the design methodology affects the choice of data structures. So, the keywords here are design, types of design techniques, brute force, sub problem solving and so on. So, let us look at algorithm design technique. What is this algorithm design technique? Now, algorithm design technique is a general approach to solve problems algorithmically, and it can be applied to a wide variety of problems from different areas of computing. So, our job in algorithm design is not to look at a particular problem and see how it is designed. We are looking at a general method of design which can be applied to a class of problems. So, why should we do this? It provides a guidance in designing algorithms for new problems, because if you find a problem that is similar to this or almost similar to this, we can get a guidance, and it represents a useful collection of tools with which to do design. So, that is why we are going to talk about algorithmic design techniques. So, there are many techniques available. Which are the most used techniques? The one that is obvious is brute force, that is, you just do not do any design technique, you just design it as it goes. Decrease and conquer, from the name itself you know that you can decrease some parameter and then try to conquer the problem. Similar to these three are similar: decrease and conquer, divide and conquer, transform and conquer. All of them are sort of taking the whole problem, reducing it in some way and making it into sub problems or so, and then conquering the problem. So, that is decrease and conquer. Divide and conquer, divide it into 2, divide it into 3 and so on. Transform and conquer, by transforming the original problem into some way, transforming it in some way, you will get a smaller problem which you can solve and conquer. Then you have greedy techniques. The basis of greedy techniques is that you try to solve a problem by looking only at the local conditions. Okay. Then dynamic programming. In dynamic programming, the basis is whatever you have done before, you store it and try to reuse it. I will come to this a little bit in detail, the conceptual aspects as we go along. Backtracking, again you solve a problem, you go one step and you find that that step does not give you what you want, then you backtrack and start from the previous point and go to another alternative. And then some genetic techniques, we will talk about this a little more as we go along. So, brute force, this brute force method is you do not use any design technique, you just based on the problem statement and definition of the concepts involved, you directly start solving the problem. So, example is sequential search, exhaustive search for travelling salesman problem and knapsack. I will be talking about this knapsack and the travelling salesman problem a little bit as we go along. Simple sort, selection sort, bubble sort. I am assuming you know what are sorts, but anyway, selection sort, bubble sort, and computing n factorial. All this you can do. Please remember that any of the problems that we talk about can be solved using any of the design techniques. It is not that you cannot solve it, but then some of the design techniques naturally fit into some class of problems. Okay. For example, knapsack problem we are going to discuss again when we are describing another design technique. So, brute force obviously you can use for any of the problems, you are just taking the problem statement and its definition, just writing the problem. So, compute n factorial where x is a real number and n is a natural number. So, this is what you want. So, this is a typical problem that you can solve. Efficiency of class is n. Compute n factorial, again the efficiency class is n. So, here we have factorial n, f is equal to 1 for I is equal to 1 to n do f is equal to f factorial into I n I, and this is p into x power. So, this is different methods of doing the these are similar problems, if you can see, that is why we have written it similar problems, but completely different problems. Okay. So, next we go, that is brute force. Next we go to what is called decrease and conquer. Now, the basic idea is you exploit the relationship between the solution of a given instance of of a problem and a solution of a smaller instance of the same problem. So, what are you doing? You are trying to say that if I have a solution for a instance of a problem, if I find the solution for a smaller instance of the problem, I can apply it here, the similarity between that or relation between that. By successfully reducing the problem's dimension, we eventually arrive to a particular case which you can solve directly without using any other, directly you can solve it without using reducing it. So, the decrease and conquer steps are as follows: reduce the problem instance to a smaller instance of the same problem, solve the smaller instance, extend the solution of smaller instance to obtain the solution of the original instance. So, this can be implemented in two ways, either as top down or bottom up, also referred to as inductive or incremental approach. Okay. Now, what is this top down bottom up? We will come to that. So, such an approach could lead us to an algorithm which is more efficient than the brute force. That is why we are looking at this design technique, and sometimes it is easier to describe the solution of a problem by referring to a solution of a smaller problem than by describing the solution explicitly. Okay. So, there are three types of decrease and conquer. So, we are talking about decrease and conquer. There are three types of decrease and conquer: decrease by a constant, decrease by a constant factor, or you have a variable size decrease. Now, what does this mean? Decrease by 1, that is you keep on decreasing by 1 till you find a solution to the trivial problem and then go keep increasing by 1 and by substituting the solution. So, insertion sort is an example, graph traversal problems, the depth first search and breadth first search are examples, topological sorting, that is in a graph how you solve it, algorithm for generating permutations and subsets, these are all solved by this decrease by a constant. Usually it can be 1, it can be more than 1 also. Decrease by a constant factor, decrease by half, decrease by like that. So, binary search and binary search, where you decrease the problem by half, solve the first half, solve the second half, join it. For solving the first half, you divide it into 1 by 4, 1 by 4 and so on. So, this is typical problems that are solved this way. Variable size decrease, the Euclid's, that is you do not it is not constantly you are not decreasing, you decrease by variable size, and this is called as selection by partition problem can be solved, the Euclid's problem can be solved. I am not going to the algorithms per se for each of one, then that will be a complete algorithm course. What we are trying to say is this particular decrease and conquer method can be used to solve these problems naturally. It actually gives you a solution to the problem naturally. Okay. So, let us take a decrease and the same power problem we can also solve it by decrease and conquer. So, you have x to the power of 2m. You can say that this will be x into x if m is equal to 1 and will be x to the squared m minus 1 into x squared m minus 1 if m is greater than 1. So, power 3 x comma m, if m is equal to 1 then return x into x, else p is equal to power 3 x, this is the decrease by a constant. You started with m, now you decrease by m minus 1 and then you return p into p. So, you will keep doing this. Okay. So, m is, let us assume m is equal to 5. Okay. So, you are trying to solve x squared 5 times power of x. So, if m is equal to 1, it is not 1, it is 5. So, you write p is equal to power 3 of x 4, okay. And then you go again, it is 4. So, x 3 and so on. And when you are coming back, you will put those values again and come. You will, when will you end this algorithm? When m becomes 1. So, when if m is equal to 1, you will return this. So, this whole thing, that the call with the last call will return 1, I mean x into x, and then you will call again and again and again. So, this is how the problem is done. Similarly, here we are decreasing by a constant factor. This is power 4 x n. So, x into x is if n is equal to 2, and if it is not, then you, if n is greater than 2, then you do n by 2 n by 2. So, that by a constant factor. So, you just see that you are decreasing the problem. What is the point decreasing the problem? You keep decreasing the problem in some way such that you reach a trivial solution. In this case, the trivial solution is if m is equal to 1. In this, the trivial solution is if n is equal to 2. So, the reduce the problem into smaller problems by a factor of at least 2, solve recursively and then combine the solution. So, insertion sort, as we already told, topological sorting, binary tree traversal recursion problem, computing the length of the longest path of a binary tree, again the recursive version, then computing Fibonacci series is the recursive version. So, let us take a decrease by 1 algorithm, insertion sort of you are decreasing by 1 n minus 2, insert a n minus 1 into the sorted list you get by calling this and return the sorted list n minus 1. Now, when you call this again, what you will do? You will do n minus 2 minus 1 and then n minus 3 minus 1 and so on till you come to a trivial case where the value will be sort a 0. So, the most well known, so that is about the decrease and conquer. Similar to that, but slight change in name is the divide and conquer. This is the most well known algorithm design strategy. You just divide the instance of a problem into 2 or more smaller instances, 2 or more. There we divided by a constant factor, but we got only one instance. Okay. Here we have 2 or more similar instances, smaller instances. You solve the smaller instances recursively and obtain the solution to the original instance by combining these solutions. So, obtain the so what you do, the difference between decrease and conquer and divide by and conquer is decrease is you are taking a problem, decreasing by 1 or a factor and solving the problem till you get a trivial solution. I mean till you come, I mean recursively call and call till you get the terminating condition as it is called. In divide and conquer you do not have one, you have 2 problems. You divide the problem into 2 smaller, at least 2 small or more also, but at least 2. So, and then you solve the smaller problems recursively again by dividing into 2 and 2 and 2 and so on and obtain the solution to the original version by combining them. So, this is the most well known design technique. So, divide to solve smaller problems recursively. The solution to the original problem is formed from the solution of the sub problems, at least 2 recursive calls in the routine. So, because you say you have to divide it into at least 2 or more. So, in the previous decrease and conquer you will have only one recursive call each time, here you will have 2, at least 2. So, in general if iterative solutions are available, recursive calls may be relatively inefficient, that is the problem. Tower of Hanoi is a typical example, merge sort, binary tree sort and so on. So, divide and conquer, you have a problem of size n, at least you divide it into 2. So, sub problem of size n by 2, sub problem of size n by 2, solution to sub problem 1, sub problem 2 and then you combine it. So, this sub problem 2 may divide into n by 4 and so on. In general it leads to a recursive algorithm. So, how does it lead into recursive algorithm? The divide and conquer, smaller instances that result in the divide step are instances of the original problem, true for a sort and min problems. If the new instance is small instance, it is solved using the method of small instances. What do you mean by this is, in our case we saw m is equal to 1 or you sort 2 numbers only. If the new instance is a large instance, it is solved using the divide and conquer method again. So, what you do, you start with a, we will assume that small instance is the terminating condition, in other words. You start with a big problem, divide into small, 2 small and these 2 small may result in a terminating or non-terminating. If it is non-terminating, again called divide and conquer. So, that is by definition divide and conquer is a recursive methodology. Generally performance is best when the smaller instances that result from the divide step are approximately the same size. So, that is why we divide it by 2. Now, let us take an example of find the min of a very large list. So, find the minimum of 20 elements. So, divide into 2 groups of 10 elements each. Find the minimum element in each group somehow, we are not telling how. Now, compare the minimums of each group to determine the overall minimum. So, what are you doing? You are taking a problem of 20, you are trying 20 elements, you are trying to find the min of 10 elements, min of 10 elements and then you are comparing the 2 mins and trying to find the min of that. Now, when we define it in recursion, you divide it into 2 groups of 10 elements each, then find the minimum element in each group recursively. The recursion will terminate when the number of elements is less than or equal to 2, that is the terminating condition. At this time the minimum is found using the method for small instances. Comparing the minimums of the 2 groups to determine the overall minimum. So, what you do? You divide it into 20 into 10, 10, then 10 into 5, 5. Each of the 10s. So, you have now you start with one problem, you divide it into 2 problems, each of the 2 problems results in 2 each. So, you have 4 problems at the second step and then each of that you divide, now you have 5 5. So, each of the 5s you divide into 2, you have 3 2 3 2 here. Okay. So, this 2 is solved terminal problem, you just compare it actually, you do not call it again. The 3 again if you want you can divide, so you will get 2 and 1 which again is trivial. So, you have landed up with 2 1 2 1 1, 2, 2. So, 6 problems which can be solved terminally. Then you take those two, find the minimum of those, go up, take those two, find the minimum, go up, and so on. So, compare the minimums of 2 groups to determine the overall minimum. So, divide the input, this is the merge sort algorithm, input the input sequence in half, recursively sort the 2 halves, basis of the recursion is sequence with 1 key. So, that is the basis, it is called terminating condition, it is called. Combine the 2 sorted sequences by merging them, we will see this with an example. So, suppose you have this, you are you have divided into 2. So, you have 8246 here and 1326, we just divided the problem, we have not done any sorting. Then you have this 8246, you divide into 2. So, you have 82 and here you have 46. Then you compare 8 and 2. So, you have 2 8 here, you compare 4 and 6, you have 4 6 here. Now, what you have to do? You have to compare these two. So, this if you take 2 as a trivial problem, because you are just doing comparison. So, out of this 2 is the minimum, out of this 4 is the minimum. So, compare 2 and 4. So, you get 2 4 6 8. Now, this 1 3 2 6 you go about 1 3 2 6. So, you have 1 and 3 and 2 and 6. You have 1 3 in order, 2 6 in order, and you have 1 2 3 6. Okay. So, now what you do? This you combine together, the minimum of those. Next we have, so now what have we done? We have seen 2 types of conquer type of techniques. One is decrease, where we had resulted in one recurrence recursive call, while divide and conquer we had at each step you had at least 2 recursive calls. Now you have transform and conquer. This is again a version of the same type. The problem is modified to be more amenable to a solution. In the second stage the problem is solved. So, for example, the problem simplification is 1, change in the representation is 1, problem reduction is 1. There are 3 techniques. So, problem simplification example is pre-sorting, finding 2 closest number in an array of numbers. So, the brute force solution is of the order of n square. If you transform and conquer with pre-sorting, you do a sorting order first and then do it, then you have the order of n log n. Change in the representation, if you represent the numbers in a particular representation, this is the data structure AVL trees, you can guarantee a order of n log n, but of course, to bring it into the representation you need some time. Then problem reduction, this all is very makes sense if you have large numbers. Problem reduction, least common multiple. So, LCM m comma n is equal to m into n divided by GCD m comma n. So, here you are doing a problem reduction using GCD instead of LCM. So, these type of transformation of the input to help you to solve the problem in a faster way is better way is called transform and conquer. So, first thing what you do, you did a pre-sorting so that you could solve the problem. The second one you represented it differently. Third time you did a problem reduction. So, you basically have the initial problem, you transfer it into another problem with a new representation, solve the new problem. So, there are 3 variations: instance simplification, representation change and problem reduction, which you already saw. So, instance simplification is reducing the problem to a simpler one. Here you have piece sorting, that is a sort, or you can have Gaussian elimination or search trees. These are some of the mechanisms that are used for simplification in a number of algorithms that are today used, like machine learning and so on. So, given a random list of numbers, determine if there are any duplicates. Brute force, what do you have to do? You have to compare every pair, and the worst case of this takes of the order of n square. Transform and conquer, what will you do? Sort the list and then compare ai with ai plus 1. So, it takes I time. So, checking of the order of n plus good sorting algorithm such as merge sort. So, it will take the order of n log n only. Transform and conquer method is much more beneficial than using the normal brute force. So, next we will go to the next topic, which is greedy techniques. Now, greedy techniques is again, as I told you, instead of looking for a global solution, look for a local solution. Why you call it greedy? That is, you are not going looking as soon as you see some optimized solution or some best solution, take it. That is why it is called greedy. So, constructs a solution to an optimization problem piece by piece through a sequence of choices that are feasible. So, that is, you take the choices are feasible according to what situation you have now. So, satisfying the constraints, locally optimal, this is what I was trying to tell you, with respect to some neighborhood definition. For saying locally optimum, you have to define something called a neighborhood. Then greedy in terms of some measure, and it is irrevocable. It is how do you say greedy? In terms of time, in terms of choice, whatever. So, for some problems it yields a globally optimal solution also, sometimes it need not. We are mostly interested in the former case in this class, that is we are not bothered if it does not give you a optimal global solution. So, this optimization you have to define by an objective function normally and by a set of constraints. So, take what you can get now strategy, that is what I was trying to say. Normally for this greedy I take a typical example of a buffet, and in a buffet you just go around and you have the cost. So, you go around, as soon as you see within that range, if you see the most costliest, you want, your aim is to eat for the maximum money. So, you take that and select it, but actually overall global this may not be the maximum, but by looking at this place this is the maximum. Like that is what is called as take what you can get now strategy. It work in phases, in each phase the currently best decision is made. That is what I was trying to tell you. Example is Dijkstra's algorithm, the shortest path is the weighted paths. Prim's algorithm, Kruskal's algorithm, minimal spanning tree, coin exchange problem, Huffman's trees. These are typical algorithms that use this greedy technique. So, we will take a example, as I told you, the travelling salesman, you cannot go through computer science without knowing some algorithms. Some of them is travelling salesman, knapsack problem and some of those shortest path problems and so on. So, here we take the knapsack problem. Now, we define the knapsack problem in two ways. You have a 0-1 knapsack problem. So, here what you do, a thief is robbing a store and finds n items. Now, ith item worth Vi rupees and weighing Wi kg. So, Wi and Vi we assume are integers. Wi is the weight of an item, Vi is the cost of the item, and W, I will tell you what W is. W is the total weight he can take. So, he can carry at most W kg. Now, which item should he take? This is the question he has to answer. So, this is the 0-1 knapsack problem. Why we call it 0-1? He can either take a item or not take an item, that is the only possibility that exists. Okay. He cannot take half an item. So, that is why it is called a 0-1 knapsack problem. The fractional knapsack problem, he can take fractions of items, whether that is allowed or not, it depends on the problem, but anyway that is how the problem is defined, he can take fractions of items. So, now let us take the knapsack problem. What is the knapsack problem telling you? We have just defined something. What we have defined, we are assuming there are n items, we are assuming that each item has value Vi and weight Wi, and we are saying that the person can take W kg, maximum of W kg. This is what we said, and we said that there are two types, either he can take an item or not take an item, or he can take fractional of the items. Now, let us assume that let us consider the most valuable load that weighs at most W kg. If jth item is removed from his load, the remaining load must be the most valuable load weighing at most W minus Wj that he can take from the n minus 1 original item excluding j. Now, what is he doing? He has all the items, then he takes the most valuable item, okay, and then so that let us assume that Wj is that item j is that valuable item. Now, what is remaining? The total W minus the weight of this Wj is the total. Now, that weight he has to take from n minus 1 original, and then from that he takes the maximum weight item, value item and so on. So, can be solved by dynamic program. Of course, not only maximum, it can at most weigh only W, that is a constraint, right. So, suppose I have n items and Wi has to, which you can choose only those items which has Wi less than W in the first case. After you remove that, which is less than W minus Wi and so on. So, that is this, this can be solved by dynamic programming. So, applicable when sub problems are not independent, here they are not independent. Bottom up, a table of solutions to sub problems is filled starting with the problem's smallest sub problems. Solution to the original instance of the problem is then obtained from the table constructed. This is a top down is a memory function, you assume you have it and then you start. So, bottom up technique in which the smallest sub instances are explicitly solved first and the results of these used to construct solutions to progressively larger sub problems. So, Fibonacci number is an example. So, what are the elements of dynamic programming? constructing solution to a problem by building it up dynamically from solutions to smaller or simpler sub problems. Sub instances are combined to obtain sub instances of increasing size until finally you have reached the original instance. So, you have to make a choice at each step, but the choice, here is the difference, the choice depends on the solutions of the sub problems, may depend on the solutions of the sub problems. For example, in our case, when we take some W A as the first, the next that you take depends on W minus W A, and you must assume that W is no longer there in your set. So, that is why we say it depends. So, principle of optimality, the optimal solution to any non-trivial instance of a problem is a combination of the optimal solutions to some of its sub problems. This is an assumption we make. And then we have what is called memoization, that is overlapping sub problems. Avoid calculating the same thing twice. That is why you usually keep a table of known results, so that if you come across those sub instances again, you can just look up the table and take the values. Next comes the next major technique. So, we have seen only one knapsack problem now, we will come to the other knapsack problem later. Next is backtracking. Suppose you have made a series of decisions among various choices, where you do not have enough information to know which you can choose. So, I am reached a point, I want to choose either this path or this path, I do not know anything now. So, I choose one. So, and each when you choose that path, you have a set of instant choices, if you choose this path, you have a set of other choices. So, some sequence of choices may be a solution to a problem. So, what is backtracking? Backtracking is a method of trying to come out from a series of decisions until you find the one that works. So, you start here, you take this choice, then you find you cannot reach a solution, you backtrack, take another choice, and then find you cannot reach the solution, then you have to backtrack from this point itself, and so on. So, you can backtrack any number of steps. So, generate and it is called also as generate and test methods based on exhaustive search in multiple choice problems, typically used with depth first state space search problems like puzzles. It is a typical tree based search problem where you have puzzles. So, you take one, you take that path, you find that you cannot find a solution. So, you remove that piece that you have put, that is why it is called a puzzle problem, go back, try another piece and so on. So, backtracking, you have state space search, initial state, goal states and a set of intermediate states, and you have operators that you can operate from that transform one state to another. Each operator has preconditions and postconditions. So, and you have a cost associated with each of the operations, and you have an utility function to tell you if you use this operator how close is your given state to the goal state. So, a typical problem is the coloring map problem. You wish to color a map with, this is another problem that you typically must know if you are talking about computer science, and that is the map coloring problem. You wish to color a map with not more than 4 colors. So, let us assume red, yellow, green and blue. Adjacent countries must be in different colors, that is a constraint. So, you do not have enough information to choose the colors. So, what you do, each choice leads to another set of choices. So, one or more sequence of choices may lead to a solution or may not also, we do not know, but we have to try. So, many coloring problems can be solved with backtracking. So, you take a choice, then you go, then you find that you cannot do that choice was wrong, go back, choose another color. Now, the solution to the problem depends upon the adjacency of the components of the map. Next is recursive problems. The definitions are recursive problem, an algorithm which contains at least one recursive call, which we have already seen. So, recursive call of the same algorithm either directly, A calls itself, or indirectly algorithm A calls B, which in turn calls A, it can be either way. So, the cascade of recursive calls is similar to iterative programming, and each recursive algorithm must contain a particular case for which it returns the result without calling itself, that is what is the terminating condition as we call. The recursive algorithms are easy to implement, but necessarily the implementation need not be efficient because of the supplementary space that is required to keep the stack. So, this is an example of the recurrence equation, the recursive algorithm and the efficiency analysis. And finally, we will come to what is called as genetic algorithms. This is again a set of optimization problems with a set of constraints and optimization function, sort of like that greedy that we saw. A solution that satisfies the constraints is feasible. So, you search for good solution among the possible solutions, but the problem is the best solution may be missed. A solution is coded by a string also called as chromosome. So, a string fitness is a measure of how good a solution it codes. Fitness is calculated as a fitness function. So, what is the three operators that you have in a genetic algorithm are selection, crossover and mutation. So, normally they talk about it in terms of generations. So, you choose the 2 parent chromosomes, that is from the set of the population, all the people in that particular population, you choose 2 parent chromosomes, that is according to their fitness. Then crossover is the procedure by which these 2 chromosomes are mated to create a new offspring. With the crossover probability, that is you have to choose the crossover in such a way that you form a new offspring. If no crossover is performed, then the offspring will be an exact copy of their parents. After doing crossover, you also have what is called a mutation. This mutation probability, after you find a new offspring, you will just flip certain bits, so that the position in the chromosome is slightly flipped, so that you get a randomness in your generation. So, you start generate random population of n chromosomes, evaluate a fitness function associated with each of the chromosome, then create a new population by repeating following steps until the new population is complete. If the end condition is satisfied, finish, algorithm is over. So, how to choose? By now, finally, what is the conclusion? So, we have seen many types of algorithm design principles like brute force, decrease and conquer, divide and conquer, transform and conquer. Then we saw backtracking, dynamic programming, and how to choose the approach by understanding the problem, by knowing the various problems and how they are solved using the different approaches. One thing I have left which is not covered here is how to solve the fractional, what is the best design technique to solve the fractional knapsack problem. So, that I leave it to you as a question, you just look that up. We solved the 0 and 1 knapsack problem. So, how to choose the approach, design approach? By understanding the problem, by knowing the various problems and what are their concepts. So, what we discuss here are the different design techniques, and we explain the different techniques using illustrative examples. We looked at some typical problems, the knapsack problem, we looked at the map coloring problem. There are many other algorithms which you will look in detail in an algorithm design analysis of algorithm course, but here why did we talk about this? Because some of the design techniques are suited to some type of data structures. So, when we talk about a data structure course, we also have to look at a little bit at the design techniques. So, that is what we did in this particular module. We will continue with the basic data structures from the next module onwards. So, thank you.